Swayam Prabha. Digital India. Educated India.
Welcome friends to this fourth lecture of week 4 of this course of environmental soil chemistry, and we were discussing about, in the last lectures we are discussing about the adsorption isotherms. Today we are going to discuss about specific adsorption isotherms as well as partitioning coefficients, and also we will be talking about the diffuse double layer. Now, what is partitioning coefficient? If you see in the slide, a partitioning mechanism is basically suggested from linear adsorption isotherms. Now, in the previous lecture we have seen the C-type linear adsorption isotherms. So, this shows the partitioning mechanism, and this partitioning mechanism, these linear adsorption isotherms are reversible, showing the reversible adsorption and desorption, and a small temperature effect on adsorption and the absence of competition when other adsorptives are added. That means adsorption of one of the adsorptive is not affected by the inclusion of a second adsorptive. So, you can see here this is a linear reaction, this is a linear type of adsorption, linear trend between the adsorptive as well as the amount adsorbed. So, basically here you can see there is absence of competition when other adsorptives are added. So, this is a special type of situation. Now, a partitioning coefficient which is denoted by this Kp is given by this formula, where Q is basically, as you know, it is an amount adsorbed, Kp is the partitioning coefficient, and C is the equilibrium concentration of the adsorptives. So, basically it is the concentration of that particular species of ion in the soil solution, and this Kp is the partitioning coefficient and Q is the amount of adsorbed ions in the soil adsorbent. So, this is the relationship between the partitioning coefficient and the amount adsorbed. So, if we move ahead and see that the partitioning coefficient provides a measure of the ratio of amount of a material adsorbed to the amount in solution. Obviously, since it is a ratio, since this Q since Q is basically Kp multiplied by C, so we can see that Kp equal to Q by C. So, that shows the ratio of the amount of a material adsorbed to the amount in solution. So, a convenient relationship between the Kp and the fraction of organic carbon, that is denoted by FOC in the soil, is the organic carbon water partitioning coefficient, which is denoted by KOC, which can be expressed by this term. So, basically KOC equal to Kp by FOC, or the fraction of organic carbon in the soil. So, this is another important fractionation or partition coefficient which is basically used for different purposes. Now, equilibrium based adsorption model. Let us discuss different equilibrium based adsorption models. Now, there are basically two widely used equilibrium adsorption models are there. One is Freundlich equation, there is Langmuir equation, and the third one we will be discussing, that is double layer models, including the diffuse double layer, Stern and surface complexation models. Okay. So, let us first talk about the Freundlich equation. Now, this Freundlich equation was first used in gas phase adsorption and solid absorption. So, here Q is Kd multiplied by C to the power 1 over n. So, here Kd is basically the distribution coefficient, Kd is the distribution coefficient, and n is the correction factor. A linear form of this equation, if you take a log, we will see this linear form of this equation, and if this correction factor n equal to 1, that means if 1 by n equal to 1, then equation becomes Q equal to Kp into C, where Kp is the partitioning coefficient, So, basically if we plot this, we will see, if we plot the log Q in the y axis and log C, that means logarithmic of equilibrium concentration in the x axis, we will see this adsorption isotherms. So, this is called Freundlich adsorption isotherms, and basically here you can see this Freundlich adsorption isotherm is used for showing the zinc adsorption as well as desorption. So, this is called the adsorption, and here you can see these are the desorptions. And this part 1 is basically refers to the linear portion. As you can see, this is the linear portion of the isotherm, while part 2 refers to the non-linear portion of the isotherm. So, this is basically example of how Freundlich equation can be used to describe the adsorption and desorption process. Now, what is the disadvantage of this Freundlich equation? Disadvantage of this Freundlich equation is it does not predict an adsorption maxima. So, to remove this drawback, Langmuir equation is basically used. Now, this Langmuir equation is developed by Erwin Langmuir in 1918 to describe the adsorption of gas molecules on a planar surface, and it was first applied to soil by Fried and Shapiro in 1956 and Olsen and Watanabe in 1957 to describe the phosphate sorption in soils. So, let us see what are the assumptions of the Langmuir equation. So, Langmuir equation assumptions are 4. Basically, the first one is adsorption occurs on planar surface. So, we basically assume the planar surface of the adsorbent, and that have a fixed number of sites that are identical, and the sites can hold only one molecule. Thus, only monolayer coverage is permitted. While discussing the basic forms of adsorption isotherms, we discuss L type of isotherm, it is Langmuir isotherm, and I told you that it is basically for the monolayer adsorption. So, this is one of the basic assumption. It is a monolayer assumption. So, thus only monolayer coverage is permitted, which represents the maximum adsorption. Second one is adsorption is reversible. Third one is there is no lateral movement of molecules on the surface, and the fourth one is the adsorption energy is the same for all sites and independent of surface charge. That means the surface is homogeneous and there is no interaction between adsorbate molecules, that is the adsorbate behaves ideally. So, most of the assumptions are not valid for heterogeneous surface found in soils, because as you know the soil surface is highly heterogeneous. So, as a result, although the Langmuir adsorption equation is generally assumed for different adsorption practices, in practical the Langmuir equation should only be used with purely qualitative and descriptive purposes because of these limitations. Now, let us see what is the equation of Langmuir equation. So, the Langmuir adsorption equation can be expressed by this, where Q equal to K into C into B over 1 plus Kc, where K is the constant related to the binding strength, Q already you know, B is the maximum amount of adsorptive that can be adsorbed, that is in the monolayer, remember it is for monolayer, and rearranging all these things you can and see it is a concentration in the equilibrium solution. Okay. So, and Q the amount adsorbed. So, rearranging to a linear form, this equation 1 becomes C by Q equal to 1 by KB plus C by B. So, basically if we, so slope is here you can see 1 by, the slope is 1 by B and the intercept is 1 by KB. So, slope is 1 by B and the intercept is 1 by KB. So, here if we put the equilibrium concentration in the x axis and C by Q in the y axis, that is amount of adsorbed, so we can see this type of isotherms. So, this is an example of Langmuir adsorption isotherms. So, Langmuir equation also can be valid for two site or two surface. So, in case of two site or two surface, the Langmuir equation is used to describe sorption data for an adsorbent with two sites with different affinities. Now, this equation can be expressed as Q equal to B1 K1C over 1 plus K1C plus B2 K2C plus over 1 plus K2C. So, at the subscript referred to site 1 and 2. So, subscript 1 refers to site 1, subscript 2 refers to site 2. So, adsorption on high and low energy site. So, if you assume that site 1 is the high energy site and site 2 is the low energy site, then we can represent this equation in this form. Now, this above equation is used to describe the sorption of soils of different physiochemical and mineralogical properties, but does not prove that multiple sites with different binding coefficient exists. So, once we have covered this Freundlich equation as well as Langmuir equation, then let us talk about the diffuse double layer, which is very important. Now, you know that clay particles have a negative charge because of different processes like either isomorphous substitution or permanent charge, or due to the pH dependent charge or variable charge. So, due to the presence of this negative charge, they adsorb cations which are positively charged. So, under dry condition, these cations are basically tightly bound to clay surface by electrostatic attractions. However, this electrostatic force depends on charge, position of the charge and valence of the exchangeable cations obviously. Now, however, one thing, when it is dry soil, then they are tightly bound because there is no water molecule. However, when they are wet, the cation adsorbed try to diffuse away from the surface due to their high concentration near surface due to the Brownian movement. So, you can see here in this picture, this is dry condition where these cations are tightly bound into the negative colloid, negative charge colloid, soil colloid. However, when they are fully hydrated, due to the higher concentration near the negative charge colloid, there will be repulsion. As a result, there will be some Brownian movement, and these positive charge cations will tend to diffuse away to the surrounding solution. So, these are two different conditions which you can see depending on either the soil is dry or fully hydrated. So, when these ions try to diffuse into the bulk solution, we will see some particular trends. So, the concentration of the cations basically decreases with distance from the surface, where that of anion increases with the distance from the surface. Obviously, at the adjacent vicinity of the surface, obviously due to the presence of negative charge in the clay colloid, there will be concentration of the positively charged cations. So, due to the diffusion of the cations, obviously as we go further from the clay surface, we will see in the bulk solution zone there will be continuous decrease of concentration of the cations, and obviously we will see continuous increase in the concentration of the anions, because anions are lowest at the immediate vicinity of the clay colloid because of negative charge. So, there will be repulsion. Obviously, as there is an increase in distance, obviously we will see the concentration of anions will be increased. So, after some distance, there will be a bulk solution. As you can see, this is a bulk solution phase. So, there will be bulk solution where the concentration of cations and anions are equal and unaffected by clay surface. So, at a particular distance where the cations and anions, you can see the cation concentration is decreasing, anion concentration is increasing. In the bulk solution phase, they will be basically equal and unaffected by clay surface. So, this is basically showing the diffuse layer or diffuse double layers. So, basically you can see here two layers. One layer is positively charged cations which are basically adjacent to the immediate vicinity of the negatively charged colloid, and further away from the clay surface there is another diffuse layer. So, you can see it is called the diffuse double layer. So, the diffuse double layer thus consists of two different layers. One is the permanent negative charge of the clay, and second is the cations diffused into the soil solution that balance the negative charge of the clay. So, that is why it is called the diffuse double layer. The innermost layers are strongly, the innermost layer is strongly held by the clay, is known as the stern layer. We will be discussing in details, and the water in this stern layer is known as adsorbed water and is more viscous than free water. a layer basically extending from the Stern layer away from clay surface is called the diffuse layer. We will see that. Now, this is a complete picture of the diffuse double layer. You can see one thing here. If this is a negatively charged colloid, you can see it is a black color. Just adjacent to the negatively charged colloid, you can see there will be very high concentration of the positive charge cations, and this is called the Stern layer. So, basically Stern layer is the layer of cations which are tightly adsorbed by the colloid, which are located in immediate vicinity of the colloid. Now, as we go further from the colloid surface, we will see the concentration of the cations are going down and the concentration of anions are increasing. So, diffuse layer is basically the layer of cations beyond Stern layer diffused due to the combined electrostatic force and diffusive force. So, the layer which is beyond the Stern layer is known as the diffuse layer, and it is basically occurs due to the combined electrostatic force and diffusive force. And finally, further away from the diffuse layer, you will see the ions in equilibrium with the soil solution. So, here these are the positively charged cations and negatively charged coions, and we can see this is the diffuse double layer. So, again this is the highly negative colloid and this is the adjacent Stern layer, which is the positively charged counter ions, and beyond this positively charged counter ion layer there is a diffuse layer. So, this is how we call it diffuse double layer. Now, let us see the different models given by different scientists to describe this diffuse double layer. Let us first see the Helmholtz double layer model. Now, in case of Helmholtz double layer, it assumes that the negative charge on the colloid is considered to be evenly distributed over the surface with a charge density of sigma. Now, the total counter charge in the second layer is concentrated in a plane parallel to the surface at distance x. So, here you can see all the negative charge are equally distributed in the surface with the charge density of sigma, and the total counter charge in the second layer is concentrated at a distance x, parallel at a distance x. So, the total if the medium has a dielectric constant of d, then the electrokinetic potential zeta is the same as the total potential psi. So, basically it can be represented by this equation. Now, the electrochemical potential is maximum at the colloid surface. Obviously, it is the maximum at the colloid surface or the clay surface, and drops linearly, as you can see it drops linearly at the location with increasing distance from the surface within the double layer. So, again in this Helmholtz double layer we assume that the negative charge is evenly distributed in the colloid surface with the charge density of sigma, and the total counter charge in the second layer is concentrated in a plane parallel to the to the colloid surface at a distance x, and if the and the electrochemical potential is highest at the clay surface, which linearly drops, and ultimately which linearly drops with increasing distance from the clay surface. So, this is the this is the Helmholtz double layer model. Now, the second model is known as the Gouy-Chapman double layer model. Now, in the Gouy-Chapman double layer model, the negative charge is again considered distributed evenly over the colloid surface. However, the counter ions are dispersed into the liquid layer as the gas molecule in the earth atmosphere, and this theory is therefore known as the diffuse double layer theory of Gouy-Chapman. So, what is the difference between the Helmholtz double layer and Gouy double layer? In case of Helmholtz double layer, they assume that the positive counter ions, that is positive ions, are basically arranged in a plane parallel to the clay surface at a distance x. However, Gouy-Chapman is saying that no, these counter ions, positive counter ions are basically diffused into the bulk solution, and with the increasing distance. So, that is why it is somewhat different than that of Helmholtz double layer. Now, what are the assumptions of Gouy-Chapman model? There are 5 to 7 different assumptions in the Gouy-Chapman model. We will see one by one. First of all, the distance between the charges on the colloid and the counter ions in the liquid exceeds molecular dimensions. Second, the counter ions, since they are mobile, do not exist as a dense homoionic layer next to the colloid surface, but as a diffuse cloud, with this cloud containing both ions of the same sign at the surface. So, they are saying that the counter ions, since they are mobile, they cannot be concentrating at a dense homoionic layer next to the colloid surface. However, rather they are diffusing away from the clay surface, and the colloidal is negatively charged, the colloidal surface is negatively charged. Fourth assumption was the ion in the solution have no size, that is they behave as point charge. The fifth assumption was the solvent adjacent to the charge surface is continuous and has properties like the bulk solution. Again, the solvent adjacent to the charge surface is continuous and has the properties like the bulk solution. Sixth one was the electrical potential is a maximum at the charge surface and drops to 0 in the bulk solution, just like in case of Helmholtz double layer. And the seventh one is the change in ion concentration from the charge surface to the bulk solution is nonlinear. This is one of the major difference with the Helmholtz model. Now, in case of Helmholtz model, the charge in the the change in ion concentration was from the charge surface to the bulk solution was kind of linear, but basically the change of ion concentration, there is no the ion concentration was basically the ions or the counter ions, the positive ions were basically arranged in a plane parallel to the clay surface. However, in this case they are basically diffusing away non-linearly. And finally, only electrostatic interaction with the surface are assumed here. So, this is basically Goy-Chapman layer, and you can clearly see that the positive charge cations are basically concentrated at the adjacent vicinity of the negatively charged colloid, and then they are slowly diffuse away with the increasing distance from the particle surface. So, surface is negatively charged, the counter ions are most concentrated near the surface and decrease exponentially. It is very important, they are exponential decay, we can see exponential decay in concentration of the positive charge with distance from the surface. Excess of positive ions near the surface should equal to the negative charge of the fixed layer, then there is a deficit of anions close to the surface. Obviously, since the surface is itself negative charge, there will be repulsion. So, there will be deficit of anions close to the surface. So, the important relationship and parameters that can be derived from the Goy-Chapman theory basically includes the relationship between potential and distance from the surface. So, we can guess basically we can get this relationship, and this relationship tan A is equal to ZE E psi by 4 kT equal to tan H ZE psi 0 4 kT e to the power minus kx, where Z is basically valence of the counter ions, tan H is the hyperbolic tangent, and E is basically electronic charge, which is basically measured in coulombs, and the psi is electrical potential in volt, and psi 0 is potential at the surface. Here psi 0 basically denotes that the distance from the surface is 0. K is Boltzmann constant, we know K, and small k is basically reciprocal of the double layer thickness in inverse of meter, and T is absolute temperature, x is distance from the surface in meter. So, by using these we can establish the relationship between the potential and the distance from the surface. Now, there is another relationship between the number of ions, that is Ni, that is denoted by Ni, and the distance from the charged surface. You can see it is basically Ni equal to Ni 0 and 1 minus tan H minus Ze psi 0 by 4 kT e to the power minus kx over 1 plus tan H minus Ze psi 0 minus 4 kT e to the power kx. Now, we know all these terms here. Ni is basically the concentration of ith ions, that at a point where the potential is psi, and Ni 0 is the concentration of ions in the bulk solution. So, this is how we can calculate the relationship between the number of ions and the distance from the charged surface. Another important relationship is there, that is the thickness of the diffuse double layer is the reciprocal of K. So, we know K is basically is the reciprocal of K, that is 1 by K. So, K can be calculated by using this formula, that is 1000 dm cube m to the power minus 3 e square Na Zi square mi summation by EKT, where these Na basically stands for the Avogadro number, Zi stands for the valency of the ion, mi stands for the molar concentration of ion, and this E stands for the dielectric constant, and E can be calculated by this formula ER multiplied by E0, where E0 is 8.85 into 10 to the power minus 12 coulomb square per joule per meter, whereas this ER is the dielectric constant of the medium. For water, this dielectric constant is basically 78.54 at 298 Kelvin. So, we can put all these values to calculate the thickness of the diffuse double layer. Now, the Gouy-Chapman theory predicts that the double layer thickness, that is 1 by K, is inversely proportional to the square root of the sum of the square root of the sum of the product ion concentration and the square of the valency of the electrolyte in the external solution, and directly proportional to the square root of the dielectric constant. So, in other words, as you can see, the concentration of ions of opposite charges to the particle basically increases. So, the concentration of ions of opposite charges to that the particles increases from 0.01 to 1 to 100 millimole per dm cube. So, you can see in case of thickness of the double layer basically decreases, thickness of the double layer basically decreases for both monovalent ions as well as the divalent ions. And so, the double layer thickness is inversely proportional to the square root of the sum of the product of the ionic concentration and square of the valency of the electrolyte. So, for both the monovalent ion and divalent ion, as you can see, we are increasing concentration of the opposite charge in the particle. So, if the monovalent cations and divalent cations concentration increases in the solution, obviously the thickness of the diffuse double layer will decrease in both monovalent ions and cativalent ions. In other words, as we are increasing the concentration of a particular cation, whether it is monovalent or divalent, the thickness of the diffuse double layer will decrease. And actually the thickness of the electrical double layer cannot be measured, but it is defined mathematically as the distance of a point from the surface when d psi by dx equal to basically 0. So, what we have learned here? We have learned that as the concentration of a particular ion increases in the solution, the diffuse double layer thickness get decreased, and this decreasing of this diffuse double layer is can be evident in case of both monovalent as well as divalent ions. So, let us see one numerical problem. So, in this numerical problem, the problem is plot the relationship between electrical potential and distance from the surface x. So, electrical potential psi and the distance from the surface x for the following values of x. So, the following values of x is 0, then 5 into 10 to the power minus 9, 1 into 10 to the power minus 9, 8, and 2 into 10 to the power minus 8 meter. So, for these three distance 1, 2, 3, 4 distances, we have to calculate this electrical potential according to the Gouy-Chapman theory. Now, given is this psi 0, that means potential at 0 distance is basically this one, mi we know, and then E also value is given, eta value is given, and then Avogadro number or Na constant is Avogadro constant is given, and also K is given, and R also given, T is also given. So, let us see how we can calculate this. So, since we have already got all this information, to calculate the potential at several distances, first we have to calculate the thickness of the diffuse double layer or K. So, here you can see for using the k we have to use this formula. So, all these values are given. So, substituting all these values we can get a value of k, that is 1.04 into 10 to the power 8 per meter. So, basically therefore, 1 by k on the double layer thickness would equal to 9.62 into 10 to the power minus 9 meter. So, we can get this double layer thickness value. Okay. So, to solve this for function, we solve this for psi as a function of x. So, basically we put all these values here, and to simplify, x equal to 0 here, and E value of k is given here, we can see. So, the thickness is given here. So, from there we can calculate this equation. Simplify, if we simplify this equation, it will turn tan h equal to tan h 9.76 into 10 to the power minus 1 multiplied by 1. So, tan h equal to 0.75. So, if you take the inverse of tan h, then obviously we will get this value, that is z is I by 4 kt equal to 0.97, and substituting this value into that equation. So, you know this equation is already been given. This is the equation. So, if we substitute the value in this equation, we will get the value of, it is substituting this value. So, from there we can get the value of psi. Okay. So, psi equal to 9.96 into 10 to the minus 2 joule per coulomb. So, again the idea of calculating this problem is to first we have to calculate the thickness by getting all the information are given. You have to calculate the thickness. Once you calculate the thickness, you have to input all this information into this Chapman equation, and you have to calculate the value of this right hand side part of the equation. Once you calculate this right hand side part of the equation, you take a tan inverse, and after that you calculate the value of the psi, and this will be basically calculated for a value of 0. Similarly, for any distance,